So this isn't, you know, some people get the wrong ideas with this, but so it's got a bunch of wires on here. Greg was giving me a real hard time with this. I won't say what I said and how he took it, but anyway. So this is just, so this goes into the system here, and it'd be nice to be able to pull this apart, but there's 4 rods in here. So imagine this is like a metal cylindrical rod, right? There's 4 of them. There's 2 of them like this, and we're going to have those both positively charged. And there's 2 like this, we're going to have those both negatively charged. It's kind of hard to explain what happens when you've got these ion fragments coming through in 3 dimensions. It's kind of difficult. So my little pea brain, I have to break it down in its individual pieces. So I'm going to look at the 2 positive rods first and how that affects ion motion. And then we'll look at the 2 negative rods, how that affects ion motion. And then we'll put those 2 pieces back together and see how does this measure individual ion fragments coming through one at a time. Right? We can't have them all coming through at the same time. We have to be able to filter through and go, okay, let's measure, let's monitor mass 1. Anything there? Nothing. Mass 2. Anything there? Nothing. Mass 3, mass 4. All the way through, all the way to mass 100 or 200. And measure each one, we would get a peak here, 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 and here. Boop! Oh, at that mass, we got a peak. We got a bunch of ions coming through. So we need to scan through all the mass to charge ratios in milliseconds before species B comes off the column. It's really amazing how they do this. All right? So let's talk about, so here's my cheesy Pictionary drawing. We're going to break it down on the other side here. But we've got 4 poles coming through. 2 are going to be positive. That's why it's called a quadrupole. Right? And we're going to have 2 that are negative in a different plane. And the ions are going to move through here. Okay? Our goal is to get the voltages on these. I'm going to talk about how the voltages work, so that only one specific mass to charge ratio gets through, all the other ones crash and burn on those poles. All right? Let's watch how this works out. Now, to understand this, which seems fairly complex, I'm going to break it down to just 2 basic non-chemical principles that you could probably teach to any 7th grader, I would imagine, right? Didn't you guys teach 7th or 8th grade? Bless you. Do you talk about electrostatic attraction? Right? Like light charges, what happens when you get 2 positives? Yeah. They repel, positive, negative attract. That's one of the 2 principles you need to understand how a quadrupole mass analyzer works. The other one, so we should be okay with that, right? Opposite charges attract, like charges repel. The other one has to do with the size difference of big ions and small ions. Would you agree with me that this ion has a bigger mass than that one, right? So what I'm going to do is take advantage of the size difference of those and how those maneuver. My favorite example is the difference between the Titanic and a speedboat. Right? If the Titanic was a speedboat, it would have never crashed into the iceberg because it would right around it, right? The Titanic, once they saw the iceberg, they're like, turn! The boat's still going straight, right? It's so big, they're like, turn, turn, turn! And by the time it just started turning, it was too late, it crashed. Right? But a small boat could have just went right around. Right? So we're going to use that one. I like the 200-meter dash as well, but I won't use that example on camera. It's fun. So let's spit these through. Let's take the first 2 poles. Let's take the 2 positive ones. So I got 2 positive poles here. And what I'm going to do is I'm going to attach a direct current to them that I can move from 0 to whatever value I want. So it's a variable DC current. I can increase it, decrease it all I want. That's what all these wires are for. Right? These are all voltage controls. And I'm going to show you why we do it, because we're going to scan through different voltages so we can scan through all the different masses, mass to charge ratios. So I'm going to connect the DC current to these babies. Right? And that's positive. So those always have that DC current. If that's all they had, let's see if this is effective as a mass analyzer. Let's say I have a small ion fragment, small mass. And let's say I have a big one, right? Just to make it simple. Big ion, small ion. Let's show how it separates these, if it does at all. So if these are positive, like 7th grade principle number 1, and these are positive, are they attracted or repelled? They're repelled. So these ions, whether they're small or big, just on electrostatic attraction or repulsion, they're going to keep away from the poles and they're just going to move straight through. It's not going to separate these ions like I want to, so that doesn't work. I need something else to help with this. So since that doesn't work with just a DC current, I'm going to add an alternating current, a radio frequency alternating current that I can change all that I want to these babies. And that goes from negative to positive, negative, positive, negative, positive, right? It goes back and forth. Now let's see what happens with these two. The fact that one's bigger than the other one. How do they move through here when this rod is now going from negative to positive, negative to positive? Now, it's got a positive DC charge, so the overall push is for these to go straight through the middle. They want to go straight through the middle. Right? That's the ultimate goal with these positive DC charges. But if I start this AC current positive, then this rod's positive and it goes right through. But once this AC current turns negative and gets to a value that's bigger than the direct current, this rod turns negative momentarily. What happens when that turns negative? Oh, so let's take this big one. Big one's going through. It's repelled by these when that's positive. Then all of a sudden the AC current becomes more negative than the DC current, and it turns temporarily negative. How well can the big one turn? It's moving in this direction. Titanic. Okay, now it's attracted to the pole. Turn. Right? It's delayed. So it goes, oh look, it's negative now. It's negative. Turn, 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 turn. By the time it turns, it's positive again. That damn AC current. So now it's positive. It goes, oh, repelled, repelled. Oh, by the time it starts hitting, oh, now it's negative. Turn, turn there. Oh, now it's positive. Now it's negative. Now it's positive. Now it's negative. And by the time it figures out what the hell it's doing, it's out and it got through. Right? That's because it's a massive ion. It can't turn very quickly. Well, let's look at the small one. We're now with a speedboat. Right? We can turn on a dime. Originally, it's repelled by both. Right? But now what happens when these turn negative? What happens? Boom! It can turn real fast. And it's straight shooting right down. It goes, ah, it's negative. Oh, now it's positive. Now it's negative. Crash and burn, baby. It's gone. It hits the rod, neutralizes it, gets sucked out. So what we effectively have done is with the AC current and the DC current, and they have ratios. I think it's a 6-to-1 ratio, but they maximize the ratios to give you the best resolution possible. The small ions get wiped out. There's a mass, based on the voltages that we pick, there's a certain mass to charge ratio where nothing below that gets through. Everything above that gets through. Pretty basic. On two basic principles that you teach in middle school. Electrostatic repulsion and attraction, and big things don't turn as readily as small things. Right? Very basic concepts. So we call this a high mass filter. I like the term filter better, a quadrupole mass filter. It's actually filtering out rather than analyzing it, right? So only the big ones get through above a certain mass to charge ratio. So if we took a look at a plot of what comes out the other end, and we drew this plot, let me do it up here. So here's the plot. So this is your mass to charge ratio, right? Here's the number of ions that get through. And based on the voltages that I set, let's say I set a DC voltage and an AC voltage, and here, everything below that gets wiped out, everything above that gets through. So these get removed. That's what I mean by a high mass filter. Everything above that, the high stuff, gets through. Right? Not too tough. Pretty basic stuff. That's just half the equation, unfortunately. Now we got the negative rods. Right? Our goal is to only allow one mass unit through. The smallest window as possible. So I need something that's going to filter out the big one.